What? June the 15th. Alright, let's do this. Oh, by the way, the issue from yesterday I figured out with the replace. I know what happens. It's when you do replace, actually let's pull this up. So when you do replace, if I put this, like access it, every time that the internally when it goes through, it will refer back not to the value pointed to this, but referred back, I think, to this thing, to this index. And it's interesting. I don't know why is that's the case. I think it just go back to referencing this index instead of referencing the actual thing. So in order for it to referencing to the actual character, you have to either do this, like char it, or you produce a temporary value, right? Just copy it out and then put it in. Otherwise it will just always go to this index. And if it goes to index, the first time when you change it, right, this index changed. So the next time when you go to the same index, right, and then it will not change anymore. So that's kind of my thought, but still, I think what happens, actually, now that I think about it, I think what it takes, it does not take the value. It's not a copy. I think it takes a reference. And because it takes a reference, of either a reference or a pointer, right? So when it could be taken, and it could not be a pointer. It has to be a reference. So take a reference of this position, right? It takes a reference. So every time I go back to check that position, and that's why it doesn't work. Yeah, a lot of times I think what in C++ they always take take references and really make you commit these type of errors. All right, maximum difference between increasing elements. Zero index integer array nums, size n. Find the maximum difference between nums I and nums j. J minus I has no absolute value. And nums I smaller than nums j. Return the maximum difference. If no such ij, return -1. Maximum difference between I and j such that I is in front of j and I is smaller than j. So what we need to find is the maximum difference. So in this case, 7, 1, 5, 4. So as I go this way, the maximum difference so we need something small on the left hand side and something big on the right hand side, right? I think maybe a monotonic array will work. Because monotonic array keep track of the current smallest, right? So in this case I have 7, that's the first one. And now we have smaller than 7, which means if there is something bigger, we definitely choose this. So it's going to be 1. And then we do 5, and then we can find something. And when we do 4, this got popped. So if you pop, you don't do anything, so you got 4. So the answer is going to be 4, right? 9432, it just keep popping, keep popping, keep popping. And if you pop, you don't really add anything. You don't do any anything. So yeah, so when you add to it, right? When you add to it, you always minus the front. Right, when you add to it, you always minus the front. And if it's something smaller comes, it will pop, pop, pop. If you pop, you don't do anything because that's just small. So let's try this one. So 1, 5 will be give you 4. 2 comes in, will pop this. 10 comes in, give you 9. Yeah, I think a monotonic array will work on this one. So let's go monotonic array. I remember the question is this: use monotonic array. But actually, I'm going to use stack for n of nums, right? We also need res equal to 0. Ooh, -1. All right. So we have something, and then we'll start popping, right? We'll start popping, and while stack.empty, if stack is not empty, right? And stack dot size -1. The last one, if it's bigger than bigger or equal to n, right? Then we'll say stack dot pop back. So keep doing this, and then we're gonna push it in. But before we push it in, we should say if stack is not empty, then we can say res equal to std maximum res and stack 0, which is the smallest, and the current one. So we do that, right? And we do stack dot push back n. And we'll do this until the end, and then we'll return the result. That seems to be the solution. All right, let's check. Oh, press the wrong button. Looks good. Let's try it. Yeah, that was good. All right, what's the tutorial on this? Prefix min. That's the same as this. Prefix min. Let's see. If this is larger than, then we do this. Otherwise, we update. Yep, that's about it. Is it better? I mean, essentially the idea is the same. Monotonic is to get prefix min. We basically save the prefix min in this variable, but yeah, we have a lot of fluff going on as well. Yeah, prefix min is a better solution, and it's not easy. It's not difficult to write. We can let's do prefix min, right? So we say use prefix min from the editorial. I don't need this. I just need premin num0, right? And then here we say I equal to 1 dot size and I plus plus. And we don't do any of this. We say if nums I is larger than premin, right? Then we say res equal to max res nums I minus premin, else we say premin equal to nums I. Well, that's fine, and then we'll return. Okay, let's try this one. Let's prefix min. Yeah, this looks good too. Yeah, it's the same thing. Okay, so that's good. We're done with this one. Now it's time to go back to solve this problem. Minimize the maximum difference. Okay, so I have Epiphany on this one. So let's pull up the problem. Yeah, this is the problem. Yeah, this is not right. This is not right. I'm gonna delete all that. So the new idea, definitely inspired by the hint. What happens is there is a little bit greedy going on. So essentially, we'll sort nums, right? We'll sort nums so we have like increasing. So we have that A0, A1, A2, whatever going on, and it's non-decreasing. And we want to find out what is the minimal max difference, right, given p pairs. So what we're going to do is we will suppose, right, the minimum maximum is a value, right? We suppose it's m. The difference is m. Now we want to count how many pairs that we can get that satisfy the requirement, which is, there's no overlapping, and the total number of pairs is at least p, right? That's it's not at least p. It's equal to p. I mean, it's you give it m, and then you find how many pairs, right? If the number of pairs is larger or equal to p, then you can decrease this value, right? And if it's smaller than p, then you need to increase this value. And eventually, because binary search will get to the point where we have the correct p. Okay, so we get that out of the way. Now the next thing to consider is how do we find the number of pairs with differences smaller or equal to m, right? Smaller or equal to this. And the epiphany is we're going to start from the first one, okay? Then we're going to compute the difference between the first two. If the first two have the difference smaller than or equal to m, then we have to count it. And if it's not, we move on. So you will say, okay, why do we always count, right? Basically, whenever we find a pair, we'll count it. Now we do that because if we don't count it, right? If we don't count it and the next pair is no good, then we have to go to the next pair, right? So in that scenario, it's always good to count the first pair, okay? So in that scenario, we count it is always better. Next scenario, if we don't count the first pair and the second pair, like this pair is good, okay? Now this pair is good, and because this A2 is already being used, so I cannot do A2, A3, I can only do, A3 and A4 and I'm going on. Which means among the first three numbers, we either take A1, A2, or we take A0, A1. So it's the same thing. So in this case, I take the first pair or I take the second pair is the same. Might as well take the first pair. So this is the proof that a greedy solution, that we always pick, that whenever we see a pair that works, we always take it. This one will work. So because of this, we have a solution. Okay, so let's code it up. I am not sure if we can do the entire explanation. This is inspired by the hints, right? We will use binary search to find the min-max difference. Let's call it m. For each search, right, we want to find the max number of pairs that we can obtain whose differences are not larger than m, right? Now, if this number is larger or equal to p, that means we can make m even smaller, right? Even smaller. Otherwise m has to be bigger. Now this fulfills the binary search requirement. Another key aspect, right? Another key aspect is to realize that after we sort nums, we should take the first pair, right? The first adjacent pair with difference no larger than m. We should take the first. We should always. Let me do this. We should always take the first adjacent pair with difference no longer than m. Now this can be proven. This can be proven the correct strategy. Because, right, if we don't take the first pair, we either have to take the second pair or the third pair, right? The third, we either have to take the second pair or the following pairs, right? If it is the case that we have to take the second pair, right, then among the first three numbers, we can only take one pair. It can either be the second pair or the first pair. In other words, in this scenario, it does not make a difference if we take the first or second pair. We might as well take the first pair. If it is the case that we have to take the third or fourth, right, pair, then it is always beneficial that we take the first pair. Yeah, this proof guarantees that a greedy solution for binary search will work. Okay, so because it's greedy, because binary search is all in long run. All right, so now what we're gonna do is we will delete everything and just basically recode the whole thing. Okay, so we have to first sort. Okay, so let's sort nums.begin, nums.end, right? We sort this, and then what we have is we need the low and high. So low will be the minimum difference. Wait, it's the minimum difference. High will be the maximum difference. The maximum difference will be I'll call it nums.size minus 1 plus 1, because it have to be something that it cannot reach. This is the maximum possible, right? So while low is smaller than high, and we say mid equal to, actually, is it possible to overflow? It is possible to overflow. Holy crap, it is possible to overflow. So we have to do, if I remember right, the low plus high minus low divided by 2. Wait, hold on, is that right? Low plus high minus low divided by 2. Yes, I think that's right. Low plus high minus low divided by 2. This is to prevent overflow. So we have a mid, okay? And then we need to count. So we say count 0, okay? Now we need to go through the nums, go through every pair. So for int I, 0i smaller than nums.size minus 1, I plus plus. Okay, so we're doing every pair. And when we do a pair, then we have to skip. You know what? If we need to skip, this probably is not the best way. Let's do this. And we do a while loop. Okay, we say while I is smaller than nums.size minus 1. Okay, so it's a while loop. Now we say if nums I plus 1 minus nums I, right, this is pairwise. If this is smaller or equal to mid, then we will say, what do we say? We say count plus plus, okay, and then I plus plus. Actually, no, I plus equal to 2, because I done this one, I have to skip the next. I cannot plus plus, I have to skip it, right? I have to skip it. Otherwise, this is when the difference is too big, and then we can just move on I plus plus. Okay, so we do this, blah blah blah. When we finish, we get a count. Then we check if count is larger or equal to p, right? That means we can afford to get it even smaller, right? So we say high will equal to mid, right? We move high to mid. Otherwise, count is not enough, right? We don't have enough, which means the difference is too small. We need to get a little bit more, right? A little bit more. So we say low equal to mid plus 1. Okay, so this eventually will get out. When it gets out is when low plus 1, it's just too small, it doesn't work, so I think we should just return low on this one. Alright, let's try. Hopefully this one works. We have a bunch of test cases, and I think I also have a wrong answer. I don't know if we put this wrong answer into it. I don't think so. Use a test case. Okay, so let's try. Yep, that looks good. That looks good. Submit it. There we go. There we go. Yeah, it's, I mean, if you just think about this binary search, it's not that hard, but pair. Greedy and binary search, exactly. This is exactly what we're doing. Greedy and binary search. One pair only, two pairs, so you always pick the first pair, right? Yeah, this and this. Greedy, another approach. Yeah, this is the same thing. Good, I think it's good. We can actually check. Sort, get this, left and right. That's fine. We get a mid, exactly the same as we do. Well, count pairs. That's fine. Writing, yeah, this is good. And count pairs, we have index, we have count. That's the same as we do. Index doing this, blah blah blah. Count index plus plus. Okay, all right. It's just a little bit trick to make it look nicer, but overall it's the same. Good. I think this is good. Yeah, I think what I forgot or what I didn't stick to is there's a kind of a rule. If it's a min max or max min, right? This type of problem, it's like 9 out of 10. It is binary search, and you get the binary search first, and then all you need to do is just figure out how to do it. I think when I was solving this problem initially, I didn't think too much about how binary search can be done. Like I thought about it, that it's a min max, it's a binary search. But then I stopped right there and I thought, well, I could solve it some other way. All right, if you take a look at this, the whole history of me solving this problem. I was having problem initially, the 2023, right? And then August to solve this again, but I was able to do it. I think that time I was able to do it directly. Yeah, binary say, what the hell is DP? I don't know why I use DP to do this, but it was alright. And then I realized, yeah, you don't have to do DP because no need DP, we use greedy. I didn't use greedy initially. That's why. Okay. And then the next time was 2 days ago. I was not able to solve it, but it was good overall. Okay, that'll be it.